Well, hello everybody. Welcome to our discussion of section 8.4, which is about the permutation event. So what is a permutation event? Let's first define it before we see some examples. So the permutation event, this refers to when order does matter. So when order does matter. This is the critical thing about permutation event. This is in sharp contrast with the topic in section 8.4, 8.5, which is coming up, and that will be about combination event, which is when order of outcomes, random outcomes, does not matter. Okay, so with these problems, we have to be careful and establish whether order of things matters or not. Okay, so before we actually cover this permutation event, I'm sure you all seen the factorial operation in mathematics, but just to be sure that everyone remembers that, I'm going to quickly cover the concept of a factorial. So let's ask the question. So first, before that, we want to cover this. But first, what is factorial? By the symbol exclamation mark. We've known that as the exclamation mark, right? In mathematics, this notation represents a factorial. So let's see how it was defined. Okay, so 0 factorial was defined to equal as 1. Why is that? There is no reason for it except that it was an agreement between mathematicians that this represents that. Then 1 factorial is also equal to 1. And 2 factorial would be equal to 2 times 1, or equaling 2. 3 factorial would be 3 times 2 times 1, 6. And I'm going to go up to 5 factorials, and I'm going to stop after that. So just to make sure that you know how this calculation is. 4 times 3 times 2 times 1 equals 24, and then finally 5 factorial is equal to 5 times 4 times 3 times 2 times 1, or 120. Having said that, please make sure that whether you're using the Casio or the Texas Instrument calculator, you know which buttons can calculate the factorial. In the Texas Instrument one, this one that I have, the button is this. Let me turn this on and clear this. The button that you can use for this to come up is this PRB. The PRB button stands for probability. So if I hit that, notice that I can now move my selection using these arrow keys. I can move my selection to NPR. That's permutation of events, which is the subject here. The second one is the combination of events. which is the subject in section 8.5. And then the last one is the factorial, and I'm moving that my selection with these arrow keys. Okay, so that, but whichever calculator you use, make sure that you know which buttons can obtain the factorial for you. Okay. So, well, let me actually do one example. So suppose we want to do 12 factorial, right? How would I do it on this calculator? First, I would enter 12. Then I would hit the PRB button. Then I would have to scroll over to the factorial symbol, right, like that, with my arrow keys. Then I'm going to hit the Enter key. Let me move this up so you can see it. So I'm going to hit the Enter key here, like that. It placed the factorial symbol right after the number 12, but now I have to hit Enter again for the calculator to run the calculation. So there you have it. So it's a very large number, right? It's over 1 billion, or is it? Let's see. No, it's not over 1 billion. It's 479,000,016. So factorials usually, they ramp up pretty quickly. So even with a Texas Instrument TI-84 calculator, if you punch in 100 factorial, it won't be able to calculate it. They have those old chips in them, so it won't be able to calculate, but a cell phone calculator probably easily calculates 100 factorial, because the chips in the cell phone calculators are usually more powerful than some of these calculators. Okay, so having said that, now we can continue with our discussion of permutations. So with permutation events, it's important to know what all permutations is. So all permutations, or let me show it with the symbol capital N factorial. Matters. Okay, so and the emphasis here is on all possible ways. That's all permutations. So the calculation of this is very easy. So if you have 5 people showing up at a line, in how many ways they can end up lining up behind, as let's say a cashier's line. Say 8 people, that would be 8 factorial. 10 people, 10 factorial. Those are all permutations, all possible ways things can be arranged along a row or a line if order matters. Okay, so let's see an example, or a few examples. So suppose we have okay, so given this scenario, we want to know in how many ways can they line up. Okay, so in how many ways can they line up refers to all of them, right? All 8 people. So that's quickly, even though this doesn't say that order matters, but at a checkout line, it does matter, right? If you're ahead of these other 7 people, you will check out sooner. So the order definitely matters. So 8, this is the case of all permutations. So 8 factorial, which is 40,320. Another way of calculating this, to making the connection between what is happening, besides the ease of calculating these on a calculator, is, well, you use the multiplication principle. Remember that? So what you would do is you say, oh, I have 8 people, so 1, 2, 3, 4, 5, 6, 7, 8. So how many people can, how many choices are there among these people to take the first spot at this cashier, at this checkout line, the first spot? Well, there are 8 spots, right? 8 possibilities. Once one of those people takes that spot, then there are 7 people available to take the second position at the checkout line, and then 6, and then 5, 4, 3, 2, 1, and this would be the last spot. So by the multiplication principle, you can multiply these together and you end up with that same number. So this is the logic behind that operation that you see there. Okay, now suppose we have an encyclopedia Okay, so when you read these problems, or when you see these problems on an exam, it's not telling you whether order matters or not, and it's going to be mixed in with problems on combination, which are problems where order of arranging, order of selection does not matter. So how to recognize which is just a matter of thinking about the context. So here we have 12 volumes, and on a bookshelf, does it matter where they end up? Yes, right? We want them to, the order matters. So if volume 1 is first and volume 2 and 3 and so on, that's a different order for these 12 volumes as if you have volume 7 first and then volume 10 and so on and so forth. So the order of arranging this on a bookshelf does matter. Okay, so that means if order matters, then use permutation. And this is, we want to know in how many ways all the volumes, all the volumes be arranged? So this is a case of all permutations. So we say 12 factorial, which would be that quantity. Again, the logic behind this, if you want to understand why this is the case, just think of it as the multiplication principle that I explained earlier. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then you simply say, well, how many choices do I have to fill this spot on the bookshelf? Well, 12. Once you pick one of those volumes and that volume ends up here, then you have 11 left, 11 choices left for this spot. Then after that, after you pick the book for that spot, you have 10 choices left for this one, and so on. So you have 9, 8, 7, 6, 5, 4, 3, 2, 1, which would be the all permutations. It would be basically 12 factorial, which we have here, like that. So that's that. Okay, a word about notations, because depending on which author's book you read, the notation that refers to permutation might be different. So here, this is a description of notational differences. The notations are different, but what they suggest, the calculation they suggest, is exactly the same. So for permutation, we have either this notation, an author might use that notation, and I'll explain what this means, or which is equal to the next notation, or they might use this notation, or they might use this notation. These are all equivalent to each other. And where, let me quickly add, where this lowercase r is always either equal to or less than the lowercase n letter. So whatever this number is always less than that, than the number that ends up in this position. Okay, so let's give an example of this. So P, and this is lowercase p, not capital letter P, which is used for probability. So lowercase p, and then 60 comma 4. This is equivalent to 60 permutation 4, or that notation. And so all of these, it refers to choosing 4 objects or entities, whatever they may be. It could be people. It could be choosing 4 out of 60, or objects or entities from a larger group of 60 such that order matters. Okay, because the notation tells us directly that this is a permutation. If this was combination where order does not matter, it would be a capital C for that case. Okay, so you can either calculate this using a calculator, we'll get to that later, or you can derive it logically on a piece of paper. So you say, well, I'm choosing 4 out of 60, and order does matter, right? So I'm going to use this scenario. So because order matter, then this choice, there are, let's call this position number 1, and number 2, number 3, and number 4. So order matters. So how many options do I have to choose for this position? 60, right? How many options do I have for this one? Once that one is picked, 59, and then 58, and then 57. So you can multiply these, and you will get 11,703,240. Okay, how would you do this on a calculator? Well, you, depending on what calculator you're using, let me make sure. Okay, like that. So we're doing 60 permutation 4. So on this calculator, I'm going to enter 60. Then I need the permutation function to activate, right? So I'm going to press the PRB button right there. The first one is already highlighted with the dashes underneath it. So I'm going to say enter to select that option. So 60 permutation 4, right? And I hit enter, and there you have it. You have 11,703,240. Okay, so that's how you obtain that using a calculator. But now with this, you know that the multiplication principle is involved in that calculation. Okay, suppose in another example, suppose we say, how many ways are there to seat 5 people in 8 seats? Assuming that the seating position matters. Okay, so here in this problem, we don't have to guess at it. It's telling us that the position matters. So it's right away, we know we have to use permutation. Now, so how do we go about this if we wanted to reason it like this? Can we do, okay, so we want to seat 5 people in 8 seats. Let's see if we can do this. If we can do 1, 2, 3, 4, 5, 6, 7, 8. So if this is seat number 1, number 2, number 3, number 4, number 5, 6, 7, and 8. If we do it this way, so then we have 5 people. So how many choice do we have to assign to this seat? We have 5. Once one of those individuals has a seat, then we have 4 options to assign here, and then 3, then 2, and then 1. What happens here? So notice in this way, we're going to run out of people before we can answer this question. So this won't work. So this will not work. So let's switch this the other way around. Let's say, okay, we have 5 people. Let's say we have 5 people, so 1, 2, 3, 4, 5. So this is person number 1, number 2, number 3, and number 4, and number 5. Okay, so this wasn't wrong, but look at these 3 spots. There's no way for us to figure out these 3 permutations without going through enormous number of manual calculations, because we have to take these positions into account as far as these people being distributed over these seats, not these first 3 seats, or these seats and these 2 and this one, and not these middle ones. So this will not help us. It's not that it was not correct, it's just not going to get us the answer we need anytime this year. But here we have 5 people. Now, how many choice does this person have to take a seat? Well, he or she has 8 options to choose from, right? Once this person takes up that seat, then how many choices does this person have to take a seat? Then that would be 7 and 6 and then 5 and 4, and that's the total number of ways these people can be seated, given that order of seating matters. Okay, so let's see another example. So here's one scenario we want to know the answer to. If books are grouped together with the French books on the left and the Spanish books on the right. Okay, so here we have a scenario where there are 5 different French books and 7 different Spanish books, and we want to know how many ways are there to arrange them on a shelf if books of the same language are grouped together. So that's a key condition for us to observe. So Spanish books are grouped together, French books are grouped together with the French books on the left, and so that's additional condition, right? And the Spanish books on the right. Okay, so let's set this up so we can understand it. So if we have the 5 French books on the left, so that would be, well, let me organize these like that. So these would be where the French books would end up. And here, this is where we have the Spanish books on the right, right? That's the condition that we are told to abide by. So for French books, we have 5 of those, 1, 2, 3, 4, 5. And for Spanish books, we have 7 of them, 1, 2, 3, 4, 5, 6, and 7. And order, of course, matters. Within each group, it matters if this book is here or there. They're not telling us that, but it's from the context, it's clear that the order matters. And ask any librarian, right? They know that it matters. Okay, so with French books, we have 5 of them. Any one of them can end up in this spot. Once that book occupies that spot, we have 4 more books to choose from for the second, and then third, 3 books to choose from, and then 2 books to choose from, French books to choose from, and then 1, right? By the multiplication principle, we multiply these, and this is arrangement within the group. Within the group, within the French group. Then here we have 7 of them, same scenario, 7, 6, 5, 4, 3, 2, 1. This would be 7 factorial, right? And this would be 5 factorial. But I'm laying it out like this so you see the logic behind why this calculation leads to these answers that we obtain. We could easily say 5 factorial times 7 factorial, but this is just more logical. Hopefully it'll answer more of your questions. Okay, so once again, by the multiplication principle, we multiply these, and this is once again arrangement within the group. Now, this middle, because the problem in this part, it specifies that French books have to be on the left and Spanish books on the right, so we are restricted to only one arrangement between the groups. What we're doing right now, what we've done with each group, that's arrangement, we're finding out the arrangement within each group by doing that. But between groups is just one. So arrangement, let's multiply that. So arrangement between groups. I want to highlight, my purpose is just to highlight the difference. So you notice what is happening. Here, we are within the group. This calculation is calculating the arrangements within this group such that order matters. And because we're restricted to these books on the left, these books on the right, then there is just one arrangement between the groups. There is no other arrangements possible between the groups. And that comes in here. So we simply multiply this by that, and we're done. And for this part. So we have, this would be, if you multiply those, you get 120 multiplied by 5,040, and this will give us 604,800 different possibilities, such that order does matter. Okay, that's permutation. So let's look at another question about the same scenario. We want to know the probability. So we just counted. Part A was just counting those number of events that fit that category. So part B, we want to know the probability of the events, or the event in part A, right? Well, we have the total number of books is 12. So all permutation would be 12 factorial. That's all possible ways you can arrange these 12 books. But for part A, we counted that many, right? So 604,800 divided by the 12 factorial, which is all permutation. So what do we get? We get 0.001263. For part C, the question is, okay. So here, notice again, like part A, we want to keep the books together. But think about how this part C is different than part A. We still want to keep the same books of the same language together, but the French books don't have to be on the left-hand side, right? They can be on the right side. So now we have the permutation within groups is going to be the same, because the French books have 5 factorial ways of arranging themselves within the same group, and Spanish books have 7 factorial ways of arranging themselves within the same group. But because now French and Spanish books are allowed to switch sides, in other words, French books can be on the left or on the right, because there's no condition here set to restrict that. The between groups, now we have 2 factorial, right? We have 2 factorial ways of arranging the 2 groups. If we had 3 groups, say Russian books, then we could say this, count the number of Russian books, say there are, say 10 of them. So multiply 5 factorial by 7 factorial times 10 factorial for Russian books, and then multiply that by 3 factorial. Where is the 3 factorial coming from? It's for accounting for arrangement between the groups such that order matters. So in this case, what we have is the 120 that we had for part A. So 120 times 5040. This is what we had for part A. But additionally, we have to multiply this by 2 factorial. Why? Let me add this. This is why I was highlighting the difference between arrangement within a group and between groups. So this, to account for the arrangement between groups, between the 2 groups. If you had 8 groups, within each group you have certain number of books, so you take the factorial of the number of books within each group for all permutation within each group, and then you would multiply it by the factorial of the number of groups that you have. So if you have 8 groups, all of that times 8 factorial. If you have 11 groups, all of that times 11 factorial, and so on and so forth. So that's where the 2 factorial is coming from, because the Spanish and the French books can switch sides. And that's how many times they can switch sides? 2, which is the 2 factorial, 2 times 1. Okay, so the answer to this question then becomes, did I calculate this? Yes, I did. It is 1,209,600. Okay, so now part D, we want to know the probability of that. Of the event in part C. Okay, same as before, we know how many of this type of event can there be at random, right? If we throw the books at random, these are how many possible ways that the French and the Spanish books can end up on the shelf when the books of each language can stay together. Now, all of that divided by all possible ways that these 12 books can be arranged on the shelf, which is 12 factorial. So 1,209,600 divided by 12 factorial, and that gives us this quantity or probability. So I carried this answer to 6 decimal places. Okay, so for example, if this question asked me to round my answer to 5 decimal places, so this 2 would become 3, right? So 0.00253 if we were to round rounding to 5 decimal places. I'm mentioning these as we go along because on the exams it's quite likely that I will ask you to round your answers to a specific decimal place on the computer before you enter it on the computer. Okay, so with this, we have wrapped up our discussion of the topic of permutation events. So we wrapped up section 8.4. When we come back next time, we will discuss section 8.5, which is the combination of events. That is when we want to arrange things at random such that order does not matter. For now, have a nice day, and if you have any questions, please post them on the discussion board.